In this class, we are going to discuss about the floating point operation. Okay, so first of all, we are going to see how our computer performs a floating point operations. Okay, which means you know that already we have discussed about the addition, subtraction, multiplication, and division algorithms, right? So that our computer makes use of binary numbers only to perform all these operations, that already we knows, right? So now we will see how our computer handles number with fractional parts or numbers with fractional values. Okay, so now the way our computer deals with fractional values somewhat different. Okay, so that means a computer can deals with the only binary that means if you are giving the decimal numbers, that will be converted into the binary format. So after that it will be stored in particular registers, that is the general format, right? That procedure already we knows. But here if you give the floating point numbers, okay, if you give the fractional values, so how our computer deals with that fractional values, how it can store. So now all those things we have to discuss here. Okay. Okay, so now let us understand it clearly. Computer represent a fractional values and it will be stored in separate register. That is also one more point. Okay, so binary numbers can be stored in one particular register, like that. Computer can deals with the fractional parts and also it will be stored in particular registers. Okay, so let us see this explanation with one example. So let us take one number with fractional value. So I can assume here, let us take one example. That fractional number I can represent it by here, 537.25. okay, here I am taking one fractional number, that is our example, we can assume. Okay, so this is not a normal number, right? So without this number we can say that 537 is a normal number, right? So that we can call it as a decimal number. Okay, so in that 0.25 is the fractional part. Okay, so this number we can call it as the fractional number, and in that 0.25 is the fractional part. Okay, so now if our computer needs to store only 537, okay, if our computer needs to store only 537, what it will do, it will simply divide with binary number. So that means this is an already 537 is in decimal number, no, directly we can say that this is in decimal. So how it will store, the computer can divide this number into the can divide this number with base 2, right? So directly we can get that binary number, right? So it will store in some register. So here 537 part is clear, but what about 0.25? okay, so in that 537 is how it will store the computer. So this 537 part will be divided with base 2, so then automatically we are getting the binary number. So how it will get, that procedure already you knows. So like that we are getting the, so 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 remainder 1 and 2 1 is 2 6 and remainder 1. So next we'll get the 2 8 remainder 0 and 2 4 remainder 0, 2 2 is remainder 0 and 2 1 is remainder will be 0. So now this format we are getting the binary number. So like that computer can store this number in particular register. So now this 537 part is clear, but what about this 0.25 part? Okay, so it will be stored in how it will be stored in computer's memory, or how our computer handles this floating point number. So now we'll see here. So now our computer represents the floating point numbers as in one format. For this purpose we can have one format, that is nothing but m into r power e. Okay, if the computer can store the floating point number, so for that purpose we have one separate format for this, so that is m into r power e. Okay, so any floating point number can be represented with a format is m into r power e. So here what is m and what is r, what is e is nothing but m we can call it as mantissa, and r we can call it as radix. Okay, and e is nothing but exponent. Okay, so here m is nothing but mantissa and r is nothing but radix and e is nothing but exponent. Okay, so now let us take a number. Okay, so this number I can consider already. So now this number I can represent, that means if I want to represent this number or if I want to represent this floating point number in this computer format, means how can we represent? So this 537.25 our floating point number. So now this floating point number can be represented in a separate format. We have computer can represent this floating point number in separate format. So that format will be as m into r power e. So this is not in actual format, right? This number is not in actual format. For that purpose I can rearrange that number into like this 0. Okay, 0. 53725 into 10 cube. Just I can arrange this number. This point can move into the 3 points to the left side. Okay, I can move this point to the 3 points of 3 points before of 3 points to the left side. Okay, so then we can get the 10 cube. Okay, so now this number can arranged in this format, right? So m into r power e. So now in that, what is m and what is r, what is e is nothing but, so m is nothing but mantissa. Mantissa can take as here m is equals to 0.53725 and r is nothing but radix. No, radix is nothing but here 10 and exponent is nothing but that is 3. Okay, so here actually what is the value? Radix and exponent already we know in normal notation. Radix is nothing but that is the powers and exponent is nothing but generally we can say that what are the power values, how much of power it consists, that is called as the exponent, right? So now what is the mantissa here? The value of mantissa, our computer take it as here 537.25, not 0. Okay, remember this point. That's why I can write it here 0.537 point. For your understanding purpose I can write it here. So no need to take that mantissa as 0 point. Okay, so here mantissa will be considered as only number. Okay, so that will be started without zeros. Okay, if you are considering 0 point, then the procedure will be terminated. Okay, so it won't take the 0 point, it will represent as 0 point. For example, if it will represent with 0 point, so then automatically that procedure will be terminated. So that's why the mantissa will be take it as only 53725 will be stored in the particular register. So now whatever computer will do means here that means it will store this fractional number. Okay, it will store this fractional number in 3 parts. That will be stored in like a mantissa part and another one is radix part and another one is exponent part. So that means mantissa will be separately stored in particular register and radix will be stored in particular separately stored in particular register and exponent will also stored in separately in one register. So totally 3 registers will take to store our one fractional number. So that means if the computer will store if computer can fractional number, that means if the computer can store the fractional number in 3 parts, that is nothing but it will take to 3 registers for mantissa purpose, radix purpose and exponent purpose. Okay, so up to this is the general procedure for floating point operation. How it will be represented in computer notation means this is the format. So now we will see how our computer adds 2 floating point numbers. Okay, so that means how our computer will perform the addition and subtraction operation in between the 2 floating point numbers. Okay, so now we'll see here. So first thing is nothing but here I am representing addition and subtraction. Okay, so now we are going to see how our computer will perform addition and subtraction operation in between two floating point numbers. Okay, so for that we have some rules. Okay, so in that the first rule will be check for 0, and the second one is alignment of mantissas, and the third one is add or subtract mantissas, and the last one is normalize result. So these are the four rules we have to follow. Okay, so for performing the addition and subtraction by using any two floating point numbers. Okay, so in that the first point is check for 0. This is the first rule. So we have to check whether the first number and second number are zeros or not. Okay, here we are performing the in between two numbers, right? Here performing the addition and subtraction between two numbers. That two numbers consist of that means whether the first number and second number are zeros or not. We have to check it. If they are not zeros, then we will perform the corresponding algorithms, that is addition or subtraction. And coming to the next one, alignment of mantissas. Then we have to align the mantissas. Okay, here we are taking the two numbers now. So for the two numbers, likewise we are having the two mantissas. First number having the one mantissa, like that another number is also having the mantissas. So for that we have to align the mantissas values. That is nothing but exponent values should be equal in this position. We have to check it, exponent should be equal. Then only addition or subtraction is possible. Remember that point. That is alignment of mantissas. And third one is add or subtract mantissas. So after aligning the mantissas, then we'll go with the addition or with respect to that algorithm we can perform the addition or subtraction operation. Okay, so and the fourth one is normalize the result. Okay, so now we'll see one by one here. So we have to normalize the result. So first of all, so that means with the help of these four steps we can perform the addition and subtraction operations on floating point operations or floating point numbers. Okay, so in that first we'll see the addition procedure. So likewise we can perform the subtraction also. Okay, so in that first step we'll go with the check for zeros. Okay, so one by one we can verify that. In that, what is the first step? Check for, this is our first step. Okay, so in that first step we need to find out the check for zeros, right? We need to check out the zeros. So let the first number present in here one register, you can assume. So here I am taking the two registers for two numbers. Okay, so first number I can consider as in one register, that is in AC, and the second number I can present in BR register. Okay, so here so let the first number is present in AC and the second number is present in BR register. Suppose assume that first number is 0. That means if first number is 0, we are checking for zeros now. So what happened if the value maybe have 0? So what happened? So assume the first number is 0 as well as the second number is also 0. Okay, so then the result is what? So result is if you are performing addition or if you are performing subtraction. So for these two operations we may get the result as again 0 only na. 0 minus 0, 0 only. 0 plus 0, 0 only. So that means the result is stored in AC register, that is equal to the 0 only. This is the first case. If two numbers will be having zeros, what happened? The subtraction and addition operation will be like this. The result will be 0 and it may be stored in first register. Like that, taking second case. If AC is not equal to 0, okay, whereas BR contains the value. Okay, so AC is not equal to 0 and also BR contains the some value. So like I can write it here, some 0.123 like that. Okay, so BR contains also value, and that means AC contains is not equal to 0 means it may be consist of some value, right, like that. Okay, so that means what is the result here? If we add AC and BR, so we'll get the result as, while performing addition or subtraction, we may get the result as, by adding these two we may get the some result, right? That result will be exist in BR, that will be transferred to the AC. Okay, so if AC is not equal to 0, whereas BR contains the value, then what is the result here means, if we add AC and BR, we'll get the result that is in exist in AC. Suppose this is an addition procedure. Suppose coming to the subtraction. Okay, suppose if it is a subtraction operation, so AC and BR. Okay, that means we have to complement the sign bit here. So AC minus BR we are performing, right? In if we are performing the subtraction means in between AC and BR we are performing the subtraction, that is minus. That means complement will be there here. We have to complement the sign bit here. Okay, so let the first number is 0. Okay, and second number is some number, some 0.123. So in between what we are performing, what we are doing, so that is nothing but subtraction. So what is the result in between will perform? So that is nothing but subtraction will perform. So then we are getting the result as 0 minus 0.123 we are getting. That means the BR contains the complement. So we have to get this result as, so 0 minus this one is nothing but again we can get the result as minus BR we are getting, right? So this number as it is we are getting, that is minus contains, right? So that is nothing but by reversing the sign bit here, AC contains the 0 and BC contains BR contains the some value means again BR we are only present here, right? So in that case there is no negative sign, but here we are getting the negative sign. That means just we need to reversing the sign bit of BR only. Okay, suppose if they are not zeros, AC having some 0.532 and some BR contains the some value that is not equal to 0, some 431. Okay, so then we are performing here subtraction operation, right? So then what is the result we are getting? So that is nothing but we are performing the subtraction operation, in between these two we may get some result. Okay, so how can we perform this subtraction operation? And likewise here also, if AC contains some value and BR contains some value, so here we are performing the addition operation, but directly we cannot perform the, if the two numbers having something value, so directly we cannot perform the addition and subtraction operation. So what we will do for that case means we will go with this second step. So in the first step we have to check it whether the numbers contains the zeros or not, that is the first step. Okay, so for that, if the number so having not zeros, that means if the two registers are not having the zeros, then we'll go with the second step. That step is nothing but here alignment of mantissas. Okay, so that means if AC is not equal to 0 and BR is also not equal to 0, for this case we have to go for the second step. So that means both the values are not equal to 0, so then we have something value, right? So other than the zeros means we have something value. For that case we can go with the, how can we perform if the two registers having values means how can we perform the addition and subtraction means we'll go with the second step, that is alignment of mantissas. Likewise, Okay, so then we'll go with the second step. So alignment of mantisses means, how can we align that mantisses? Just now I explained alignment of mantisses is nothing but that the conclusion part is exponent should be equal. That is the logic here. Okay, so let's take two numbers here. Okay, so let the first number I can consider as, that is AC is equals to some fractional part I can consider. So here I have one number, no, I can consider this number only. So 537,251 into 10 cube. This is one number I can assume, and one more number like that second number I can assume, that is nothing but 0 point, so 1 2 3 triple zeros into 10 power minus 1. So here I can assume two numbers ma. So the two numbers as contains AC and BR registers. Okay, so now we have to perform the addition and subtraction operations in between these two numbers. So before performing this addition and subtraction operation, we have to check for the zeros first. Okay, so here AC is not equal to 0 value and BR is also not equal to 0 value. So we have to align the mantisses directly. Okay, so that means here the exponent value should be equal. So what is the logic here? Exponent should be equal. Okay, so what are the exponents we are having? The first number exponent will be 3 and the second number exponent will be minus 1. So here both will be different exponents we are having. We are not having the equal exponents. For that case, we have to align the mantisses. Okay, we can arrange the exponent values. For that case, we can align the mantisses. Okay. Okay, so here the first number of exponent will be 3 and the second number exponent will be minus 1. So we have to alignment the mantisses, these two. We have to alignment the mantisses in such a way that the exponents of these two numbers must be equal. That means the exponent may be either 3 or maybe minus 1. Okay, so we have to make those two exponents are equal. So then only we can perform the addition and subtraction operations. Okay, that means if the exponents are equal, so then only we can add or subtract the two mantisses. Okay, so now let's see how we can align the mantisses in such a way that both the exponents are equal. So now we'll see here. Okay, so here there are two possibilities will be there. We can make that first exponent as maybe 10 power minus 1, or we can make the second exponent as 10 power 3. That is the two possibilities we are getting. The first number exponent may be 3 as minus 1, or the second exponent as minus 1 to 3. Okay, so like that we have two possibilities. Okay, so let us make that first exponent as 10 power minus 1. Okay, here I am considering the first approach. We have two possibilities now, so in that I can consider the first approach. Okay, so let us make the first exponent that as 10 power minus 1. That means here I can consider 10 power 3 as 10 power minus 1. Okay, so the difference between 3 and minus 1, what is the result? So the difference between 3 and minus 1 is nothing but 3 plus 1 4. So totally we have the difference is 4. So 4 bits what are that 4 bits means? Here we have to move the 3 2 1 0. After that we will get the minus 1 no. So that means we have to move the 4 bits here. Okay, so now let's see that first approach, the difference between these two exponent as 4. Okay, in the first approach let us make 10 power 3 as 10 power minus 1. So then only the two exponents are equal. Okay, so how we can make the two exponents are equal means, here the first approach, that is 10 cube as 10 power minus 1, for that we can perform the shift left operation. Remember this point, this is very important thing. For that first approach we can perform the shift left operation. and also by decrementing the exponents. This is the major point. Okay, for that first approach we can perform the shift left operation and decrementing the exponents also. So we know what is that shift left operation, right? Zeros will be abandoned to the right side and all the bits are shifted to as per positions or as we want to the left side, right? So here the difference between the 3 minus 1 means 3 plus 1 is means 4. So we have to shift each bit 4 positions to the left side. Okay, here we'll get the difference as 4 now. So we are performing the shift left operation. For that the zeros will be shifted. Okay, zeros will be added or abandoned to the right side of the first number. Okay, and also the bits are, that means each and every bit will be shifted as we want to the left side, as per position as we want to the shifted. Okay, so here the difference is 4 now, so I can shift that 4 positions. Okay, so just observe that. So that what happens if you want to shift the 4 bit positions means automatically the MSB bits, automatically the first 4 bits of the MSB bits will be lost. Here we are performing the shift left operation, right? So shift left operation is nothing but we can adding the zeros on right side part and left side bits almost lost. That means here we are adding the numbers. After 5 1 we are adding the 4 zeros. What about the 4 MSB bits of the first 4 MSB bits means that will be lost. Okay, so this 1 will be shifted to the 4 position to the left. Likewise this 5 will be shifted to the 4 position to the left side, not right side. You can shift the left side. I can show it how can we shift the data. So AC is equals to, we have to shift 4 positions, right? So 4 positions means first 4 bits will be lost, right? So automatically what we will get the information here, 0 point, as it is 0 point. So what are the remaining bits we are having? 4 bits are lost. So 5 1 and we are adding 4 zeros on the left side into, okay, so this is our number we are getting. That means while performing shift left operation what will happen means here the 4 bits of the MSB bit will be lost. Okay, so that means each after that whatever the number we are having, so after 4 bits whatever the result we are having, that will be shifted each position to the left side. Okay, and the right side the zeros will be added. How many bits we are how much of difference we are having, that much of difference of the zeros will be considered as the right side position. Okay, so now let us take that power value. So power value is nothing but here we are removing the 4 bits, right, and we are adding the at the left side right side 4 zeros. Then automatically here 4 bits will be decremented. We are losing the 4 bits now, that means decrementing the count. So automatically, so 3 will be lost, 2 will be lost and 1 will be lost and 10 power minus 1 we are getting. Okay, so 3, 2, 1, 0, 4 bits lost. These are 3, 2, 1, 0. What are the 4 bits means? These are the 4 MSB bits we are lost. Okay, so then we are getting the 10 power minus 1. So that's why we are performing the here in first approach. If you are performing the higher exponent as converted to the lower exponent, so you can perform the shift left operation and decrementing the exponent value. Okay, so now let us take the second number. So BR is equals to, this second number already in 10 power minus 1. So no need to change that value. So directly you can consider as it is. 1, 2, 3 and 3 zeros we have into 10 power minus 1. So now both the exponents values will be equal. So after alignment of the mantissas, then we will go to perform the addition and subtraction operations. Okay, so how can we perform the addition operation means as it is 10 power minus 1 bases both will be same, you can consider anyone in that. So now add all the values. Normal addition procedure we know now, you can add it. 3 plus 0 is nothing but 3, 2 plus 1 is 3 and 5 plus 1 is 6. So and 0 plus 0, 0. So now the result will be, we are getting this one. So this is the first approach. Okay, so now coming to the second approach. Second approach is nothing but this 10 power minus 1 as 10 power 3. What happened? So how that exponent will be converted into like this, means what is the procedure we are having, now we'll see. Okay, let us take second approach. Clearly I am writing here 10 power minus 1 should be 10 power 3. Okay, so 10 power 3 as 10 power minus 1, that is first approach. Now coming to the second approach. So for this second approach, so how can we make it, means by performing the shift right operation, exactly opposite to the first approach. Shift right operation and incrementing the exponents. This is the major point. Okay, so in shift right operation, what will happen means, in shift left operation we are adding the zeros on right side, right? But here in shift left operation we are adding the zeros on the left side of the original information. Okay, so what will happen means zeros will be abandoned to the left side. So the second number will be become as, here what is the second number we are having, Br is equals to 0.12300 into 10 power minus 1. So now this 10 power minus 1 as converted to the 10 power 3. So for that we make it as, we'll take it as shift right operation. So what we will do here, shift right operation, the zeros will be abandoned to the left side. Okay, zeros will be abandoned to the left side of the original information and also incrementing the exponents. So now this information will be converted as like this. That means one position, that 0 will be added on the left side, automatically one position will be shifted to the left side. So here 0 point, so we have to write it as 4 zeros because here minus 1 and here we have to convert it to 3. So minus 1, 3, what is the difference again? 0, 1, 2, 3. The 4 bits will be present. So for this 4 bits we have to add it 4 zeros on the left side. Here we are adding the right side actually. Here we are adding the left side. Okay, so automatically what happened means, in that second approach what happened means, the least significant bits of the 4 bits, 1, 2, 3, 4. So the least significant bits of the 4 bits will be lost.